In this video, we're briefly going to discuss the thought process you might go through when determining whether or not you should look at a frequency table using counts or convert it to rates, and if you should use an equally weighted average, unequally weighted average, and those sorts of questions. Unfortunately, there is no hard and fast rule. There's no official or even semi-official flowchart to present that says, oh yes, in this kind of circumstance, here's the approach you should use. Rather, you have to think about what it is that what kind of story you want your data to tell, and whether or not that story is being affected by some other variable that you need to take into account. So hopefully through this example that'll make a little bit more sense. Here I have a very hypothetical and simplistic example of 4 locations, very originally named A, B, C, and D. Each of those locations have 4 populations. They get tenfold bigger each time. The tenfold doesn't really matter, it just looks pretty. And we have some COVID deaths, because why not? And they also get 10 times higher each time. So we could imagine asking a question such as, well, what is the mean number of deaths across these locations? So we're just looking for a mean, and by mean, unless we specify, perhaps we go the easy way and we'll just calculate kind of the average. So this is an equally weighted mean, the normal average, the average you would have done before taking Math 105. And we get a number. So by taking a mean, remember means and medians and modes, all of those are measures of central tendency. So we're saying, here's this number that in some way is the best numerical summary we have of this data. So if we had to choose a number to represent the number of deaths across locations, it would be 556. Well, that's kind of weird when you look at it, because we have, of the 4 locations, 556 is greater than 3 of them. And it is substantially less, almost a quarter, of the last one. So yeah, maybe it's representative value, but one could argue it does not do a very good job of representing these values. So we learned an alternate way of doing that, of doing a weighted mean that takes into account some other variable. And perhaps that makes sense in this case. We have another variable, it's population. And so we can see in this location D, where we had a large population, we have a large number of deaths, and a small population gave us a small number of deaths. So clearly, just eyeballing this, there's a relationship between deaths and population. So maybe it makes sense to have our measure of central tendency, our summary here, somehow take into account population. And the way that we learned how to do that was by doing a weighted mean instead. And the weights are the whatever variable we want to control for, which is generally population, at least in the examples we've been doing. So we do this by, or at least we do this quickly, using the sum product function. So we highlight the things that we want, our actual values, comma, highlight the weights, and this will do, it's a shortcut for this times this, plus this times this, plus this times this, plus this times this. That sum product function is a shortcut for all of that. And then we have to divide by the sum of the weights, which is population, and then hopefully that will account for the effect of population on our COVID deaths. So if we do this, what happens? Well, we get a number, but we should always look at our numbers and see if they make sense. Now we have a number about 1800, which is much, much closer to this one, location D, and much, much further away from these two. So from a mathematical standpoint, that makes sense. We took our original data and we are assigning a relative importance based on the population. Well, location D had the highest population, so we're saying this death is the most important. We're going to give it the most weight. And so our summary statistic should follow this value the closest and follow these less closely. And that's exactly what happens. So our value is 2000. When we follow it closely, we get 1800. That is pretty close. Unfortunately, it is arguably even less of a good summary of the average of the representative number of deaths across the 4 locations. I mean, sure, location D had a larger population, but should it be more important in this data set? Like, does that make sense for the question that we're asking? Specifically when we're looking across all 4 locations and we want a number of deaths? I would say probably not. And honestly, neither of these values do a particularly good job of characterizing COVID deaths across the 4 locations. So that being the case, then perhaps we're asking the wrong question. We're looking at the wrong numbers, and it's not the number of deaths that we need, but it is in fact the death rate. So it is the number of deaths per number of people who could have died. So it's a ratio, it's a proportion. Sometimes this appears as an empirical probability, but not in this particular case. Right now, even though we would calculate it the same way, it really is just a ratio. So as I said here, this rate would be number of deaths per number of people who could die, and that per number of people is the population. So if we were to calculate a rate, because it is a proportion, we have one thing divided by a number, or one thing divided by another thing. Here we want the number of deaths divided by the number of people who could die, the population. And so we get a rate. We can then calculate this for all of the other locations. So the rate, kind of like what we were trying to do with the weighted mean, calculating the rate is also a way of taking into account a second variable, and again, especially population. So by calculating rate, we have this deaths, but we are correcting it in a way of thinking. We're kind of correcting the number of deaths for the population. We have more deaths when we have a larger population. That kind of makes sense. So if we convert things to a rate, then we take into account the fact that there's a difference in populations. So let's calculate the rates here, and we see, imagine that the rates are actually the same for all of the locations. So instead of trying to take an overall average and use that, or use population through a weighted mean to do a correction, instead, if we calculate the rate, we can do a population-based correction, if you will, of each location independently and get a number. And now we could compare these, and we see we don't have to calculate an average. We can see, well, they are all the same number. And so it makes a lot more sense in this example to compare our locations using rates, because there was some inherent difference between locations that we needed to account for, and we couldn't effectively account for those just using the mean. We had to convert it to a rate first. So kind of a site-specific correction. Maybe that's the best way to think about it. Okay, hopefully that helped.